possible. All right, so now we're going to go to the concept of curvature. All right, so what I wanted to start with here is just a basic function that you'd be familiar with, just a 2D f of x. And what I want us to do is try to notice some things about where we would classify this function as having the most curvature, right? I think we would agree that there's kind of seems to be a lot of curvature right in here, right? Really kind of curvy there. It's kind of curvy right here. Same thing here, and same thing here. So what I have graphed here are f prime is this dashed line, and then the little tiny dashes is f double prime. So what do we notice here? Well, the thing that I notice is in this region of high curvature, I'm seeing f double prime being very much further from 0 and f prime being very close to 0. Same thing right here. F double prime is further from 0. F prime is very close to 0. In this, right? Oh, I don't know, I didn't want to write that. But we can see that f double prime is further from 0. F prime is closer to 0. Same thing here, high curvature. F double prime is far from 0. F prime is really close to 0. So the big takeaways here, it seems like you get the most curvature when the second derivative has an absolute value that is big, and f prime has an absolute value that is very small. So we're going to get to both the idea of f prime and f double prime and how they both play in. Right now, at first, I want to just focus on the fact that the second derivative's absolute value being big kind of tends to give me more curvature. So with that idea floating in our heads, here's how we are going to define curvature. Curvature is the derivative of the unit tangent vector with respect to arc length. Okay, so a couple of things to remember. The unit tangent vector is the tangent vector, or r prime, divided by its magnitude, right? So it's always got length of 1. So let's understand why this makes sense for curvature. So let's make a curve here that's got a lot of curvature here, and then a lot less here. Okay, so there we go. All right, so in these areas of high curvature, if I draw a unit tangent vector right here, and then I draw a unit tangent vector near it right here, what you notice is that as the arc length changes, right, as I do a little bit of a change in how far I've gone, the unit tangent vector changes drastically. So what we can say is that this quantity is big because there's a huge change in the unit tangent over a very small arc length. Whereas down here, where you have a lot less curvature, there hasn't been a very big change in the unit tangent as you change the arc length. So you can see that this definition makes some sense, right? That high curvature is going to cause a big value in this quantity, and small curvature is going to cause a smaller value, because remember, this is saying how does the unit tangent change as the arc length changes. Now here's the only problem with this. Most of the time when we're given a vector function, we're given that vector function parameterized with t. So what I would rather do is be able to define curvature using t instead of s, right? Using the parameter value t instead of arc length. So down here we have some insights. First of all, if you take the derivative of the unit tangent with respect to t, you can write it as the derivative of the unit tangent with respect to arc length. and then times it by the change in arc length over change in time, or the derivative of arc length with respect to time, right? What is this? This is the chain rule, right? And you can kind of see that if you canceled out ds, then you would end up with what's on the left. So then if I solve for this, right? Solve for this, because this is what I have up here, then you get that this is equal to the quotient of derivative of the unit tangent with respect to time and the derivative of the arc length with respect to time. All right, and then I don't know what happened to my fraction bars here, but there we go. So then curvature then can be defined as the absolute value of this derivative with respect to time over this derivative with respect to time. Okay, but what is the one on top? Well, we can just shorthand that as it's the magnitude of t prime. And then on bottom, that's the magnitude of r prime. So this one is going to be a much more useful formula for us to use, because we are going to have our vector functions defined as functions with respect to time. All right, or I always like to say time for t, but with respect to t, but if you want to think of it as time, I think that's helpful. All right, so let's calculate the curvature of this equation. So what I want is I want a curvature function. It's going to depend upon t, so this will be really handy because I'll be able to determine at any t value on my curve what is the curvature at that point. All right, so what we just learned is that we are going to need to find the derivative of the unit tangent with respect to t and the derivative of the arc length with respect to t. But as we saw on the last page, that's just the, and sorry, that is magnitude. So that's the magnitude of t prime over the magnitude of r prime. So we got to set about figuring these things out. So we already have r of t, so let's start with r prime of t. So that's going to be 2t, and then when I multiply 4/3 by 3/2, and get some nice cancellation here. Oops. Take one away from the exponent. So this will be 2t. This will become 2, and then t to the 1/2, or the square root of t. Doesn't matter. So there's my r prime. Okay, but I don't just need r prime, I need its magnitude, right? So the magnitude of r prime of t, that's going to be the square root of 2 squared plus t squared plus 2t to the 1/2 squared, which is 4 plus t squared plus 4t in this case. Now, if I could simplify this more, that would be great. And in fact, in this case, I actually can. So this is going to be, if I put this in its descending order, it's going to be that. And this can actually simplify to t plus 2 squared. This is a perfect square here. And because t is always greater than or equal to 0, when I take the square root of this square, I can just say it's equal to t plus 2. So that's nice. This is my r prime is pretty straightforward. Okay, so now let's talk about the unit, the derivative of the unit tangent. So first of all, remember the unit tangent itself. The unit tangent itself is r prime of t divided by its magnitude. Okay, I need to figure out the derivative of this. So first of all, let's get this written out. So r prime of t is 2t, 2t to the 1/2, and then r prime is t plus 2. So I can combine all this into 2 over t plus 2, t over t plus 2, and then 2t to the 1/2 over t plus 2. That's just my unit tangent. What I need is to take the derivative of that. All right, so we'll go t prime then is going to be, so now we just got to take derivatives. So this guy, first of all, is we should probably go ahead and get this ready to have its derivative taken. So like right here, this should really be written as t plus 2 to the negative 1, right? And then in these other two here, I suppose what we could probably just do is do a quotient rule, so I can leave those alone. Okay, so that's still my t. All right, so then t prime, maybe I better give myself some space so it doesn't all run together. So t prime in that first case is going to be negative 2, t plus 2 to the negative 2. And then as I do the quotient rule here, right, we're going to have 1 derivative of the top times t plus 2 minus the top times the derivative of the bottom, so times 1, all divided by t plus 2 squared. So that's just me performing the quotient rule. And then we can do the same thing over here. So this will be the derivative of the top, so that'll be 2 t to the, excuse me, not 2, 1 t to the negative 1/2, applying the power rule to the top, times t plus 2, and then minus 2t to the 1/2 times 1, all divided by t plus 2 squared. And so now we just have some, some cleanup work to do here. So t prime, so here we're going to have negative 2 over t plus 2 squared. And then we'll have, so here we're going to have t plus 2 minus t, so that's just going to be 2 over t plus 2 squared. And then we have a little bit more going on over here. So what I would suggest here is understanding that we probably need to deal with this t to the negative 1/2 here a little bit better. So what I'm going to do is break this apart at first. So this will be t plus 2 over, and I'm going to put this t to the 1/2 on the bottom, t plus 2 squared. So what I just did here was just took this one and wrote it over here. And then this one over here minus, I would really like to have the same denominator. So here's what I have right now. Right now I have 2 times t to the 1/2 over t plus 2 squared. That's what exists right now. To get a common denominator though, I could multiply by t to the 1/2 on top and bottom. And then I would have that common denominator that I want. So here's my t prime. So we're going to have, this is going to become 2t. So it looks like we're going to have t plus 2 minus 2t. So this is going to be 2 minus t. And on the bottom we'll have the square root of t, t plus 2 squared. So that's my unit tangent vector's derivative with respect to t. Okay, but that's just t prime, right? What we need is the magnitude of t prime. So, and I realize that I've run out of room here. I really hope that you used your space better than I did. It's a little bit hard on the computer here. But what we'll do here is we'll take the magnitude of t prime, and because I've run out of space and because I trust you can do some algebraic simplification, we'll take some liberties here and not do too many steps, but I'm just literally going to take all of these terms, or all of these components, square each one. And I'm just going to ask you to trust me that after I do a lot of simplification, so we'll just say simplify a lot, what we end up with here is t plus 2 over the square root of t. Sorry, not t plus 2 on top. It's just going to be 1 over the square root of t plus 2. So all of that does, in fact, break down into that, I promise. Good little exercise for you to try it. It's not too many steps. But then, after all of that, we get the curvature then, right? We know that's the magnitude of t prime over the magnitude of r prime. And that is equal to, we're going to have 1 over square root of t plus 2. And then remember that r prime ended up being t plus 2. So this is going to equal 1 over the square root of t plus 2 squared. Okay, so there's our curvature function. So let's think about what this means. The bigger t gets, the bigger the denominator of this fraction gets, and so the smaller the curvature is. So we can just make a little comment. As t gets large, the curvature gets small. All right, so let's see if that actually bears out. So I'm going to go ahead and go back to our grapher real quick and see what this thing looks like. So we've got 2t, t squared over 2, 4/3 t to the 3/2, and we're going to go from 0, I don't know, maybe up to 5 or something like that. Okay, so we've got that, and actually let's go less. Let's just go from t equals 0 maybe to 2. Okay, and so what you can see is really there's not a ton of curvature anywhere, but what happens definitely is the bigger t gets, maybe go ahead and go even higher, let's go to 5, the bigger t gets, the less and less curvature we have. More curvature down here, far less way out here. So so we're seeing that, yeah, as t gets big, we're expecting not very much curvature at all. Now that process we just went through was admittedly pretty rough. Finding a unit tangent vector and then having to take its magnitude is, in most cases, algebraically miserable. So what would be nice is if we could skip it. So this formula on the next page here gives us a way of doing that. So I'm not going to do a proof of this. It's just, it's just kind of ugly, and I don't think it would be a great use of our time. But it turns out that this also gives the exact same thing, and it avoids using the unit tangent vector. So this is probably the formula that we're going to use most often. So what I want to do real quick is take the example that we just did and use this formula to come up with the curvature, and we'll see that it works much easier. So on the previous page, we already determined r prime of t was 2 t and 2t to the 1/2. So this formula asks us to also do r double prime. So we can do that. So that'll be 0, 1, and then we've got t to the negative 1/2. Okay, so it wants us to take a cross product, so we can do that. So we'll do our I, j, k. So we have 2t to the 1/2, and then we have 0, 1, t to the negative 1/2. So if I take that cross product, for the x component, I'm going to end up with, well, t times t to the negative 1/2 is t to the 1/2 minus 2t to the 1/2. That's my x component. Then my y component is going to be, well, t to the 1/2 times 0, so that's 0 minus 2t to the negative 1/2. And then for my j component, it's going to be 2 minus, or excuse me, my k component, 2 minus 0. So this is just going to be negative, and I'll go ahead and turn this in, instead of t to the 1/2, we'll say square root of t. And then negative 2 over the square root of t, and then 2. That's not so bad. But we need the magnitude of this, right? So the magnitude of r prime cross r double prime, that'll be the square root of negative root t squared plus negative 2 over root t squared plus 2 squared, which is going to be the square root of t plus 4 over t plus 4. And then if we get a common denominator here, this will be t squared plus 4 plus 4t all over t, getting a common denominator for everything, which is square root of t plus 2 squared, when I factor that out, divided by the square root of t, so that's going to be t plus 2 over root t. And then from the previous page, remember, we already knew that r prime of t is, its magnitude is t plus 2, right? We knew that from the previous page. So we can then take our curvature and say, okay, it's this magnitude of this cross product, so that's t plus 2 over the square root of t, divided by t plus 2 to the third. But that simplifies precisely into square root of t, t plus 2 squared, as one of these cancels out with one of those. And so this gives us a path to, there's still some calculation to do here, but trust me, in almost every situation, it's much easier to not have to deal with the unit tangent vector. It's often a pretty big pain. All right, let's do one other example here. Now, often what we're going to do is just try to figure out our curvature at a particular point, and that's usually a lot more friendly to try to figure it out at a particular point, because it doesn't. You don't have to carry variables throughout all your calculations. So we'll see how this is quite a bit easier. So we are going to use the formula that we just learned, however. So we know that we need to figure out, right, what is r prime. So as I look at my components here, r prime is negative 1 in the x. It is e to the t minus 4, right? The chain rule doesn't yield anything other than 1 when we take the derivative here. And then 8 minus 2t. So there's my r prime. r double prime of t is equal to 0, e to the t minus 4, and then negative 2. All right, now they want us to do this at the point negative 1, 1, 16, right? So we got to know what t that's actually associated with. So we're going to set 3 minus t equal to negative 1, e to the t minus 4 equal to 1, and 8t minus t squared equals 16. So here it's pretty apparent that t should be 4, right? In order to make this equal negative 1. T should be 4 in order to make this equal 1. So if we put 4 in here, that should equal 16, and in fact it does. So that means we need to do this at t equals 4. So what I really need is r prime of 4. So here's where I get to make everything numerical. If you plug 4 in for t here and here, you get 1 in the y and 0 in the z. And if you plug 4 in for t in r double prime, you get 0, 1, negative 2. So you can see one of the appeals of this is now when I take my cross product, I don't have to worry about I don't have to worry at all about coming up with you know, I don't have to worry about variables or anything. I can just take the cross product of numbers, which is a lot easier. So my cross product, r prime of 4 crossed with r double prime of 4, that ends up giving me negative 2. Let's see, negative 2 and negative 1. So then the magnitude of that negative 2 squared plus negative 2 squared plus negative 1 squared all just turns out to be 3. And then you have your r prime of 4 that you need to take the magnitude of for the formula, but that's just going to be the square root of negative 1 squared plus 1 squared plus 0 squared, so that's just going to be the square root of 2. So then that means that my curvature at 4 is going to equal 3 divided by the square root of 2 cubed. And the square root of 2 cubed is the square root of 2 squared times the square root of 2, so that's just going to be 3 over 2 roots of 2. And that's my curvature at that particular point on the curve given. Now, one other thing that we want to address then is, you know, this is Calc 3. We have learned how to take, you know, this curvature of these space curves, but does this apply to curves in 2 dimensions? And the answer is yes. So what you can always do is if you have just a basic y equals f of x function, what we can do is you can actually write it as a vector function if you put x as the x component and f of x as the y component. And then what you can observe is that r prime of x is 1 f prime and r double prime is just f double prime. And so if you kind of did this and artificially talked about k being the k component or the z component being 0 at all times, then you can go ahead and apply the formula that we had. So you can do I, j, k and do a cross product with 1 f prime 0 and with 0 f double prime 0, right? So I'm just using these formulas that we made note of up here. Okay, and so when I take that cross product, I end up with 0, 0, f double prime. And so then the magnitude of that is just going to be the absolute value of f double prime. Because it'll be the square root of f double prime squared, which is the magnitude of f double prime. And then r prime of x, its magnitude to the third power is going to be 1 squared plus f prime squared plus 0 squared to the third power, which is equal to 1 plus f prime of x squared, and then changing the square root to 1/2, it'll be to the 3/2. And so that's where you get this formula here. So you can actually compute the curvature of a function in the xy plane at a particular point. So it says compute the curvature at x equals 0, 1, 2, and 3. All right, so what we just need to do is find f prime and f double prime. So f prime of x, it's easy enough, 3x squared minus 6x. And then f double prime of x is equal to 6x minus 6. And so we know that the curvature as a function of x is going to be the magnitude of 6x minus 6 divided by 1 plus 3x squared minus 6x squared, all raised to the 3/2. But what we can do is we can go ahead and plug in all these values here. So the curvature at 0 is going to be -6 over, it'll just be 1 to the 3/2, so that's just going to be 6. When I do the curvature at 1, that's going to be 0, right? Because it'll be 6 times 1 minus 6, all over 1 plus 3 times 1 squared minus 6 times 1. Right, but all that matters is the top is 0, right? So you get 0 there. And then I can, let's do k of 2, and I'm kind of running out of space here. 6 times 2 minus 6. Move this just a bit. And then 1 plus 3 times 2 minus 6 times 2 squared to the 3/2. But guess what? That's 0. So this is just going to end up being 6 again. So you got these different curvatures of 0, 1, and 2. And let's see if this makes some sense to us. So we can graph this. So here's our curve. So we'll type in x cubed minus 3x squared plus 4. And take a look at the graph here. So remember what it said is at x equals 0. Remember that's where we had a curvature of 6. We have quite a bit of curvature there. At x equals 1, it's telling me I have no curvature, and I think I would agree. And then at x equals 2, I've got that high curvature once again, right? So you can see this thing at play. Now, something that I thought would be interesting, and I kind of have my notes all out of order for some reason. So if you would, in the notes, go to example number 7 for a moment. So you're gonna have to skip a couple of pages. So in example 7, this isn't something I'm gonna actually ask you to do in homework or on a test, but this is really cool because I think it kind of helps us understand this measurement of curvature that we're doing. What is it actually, what is it telling us when we get a number like 6 for our curvature? So one of the ways that we can quantify curvature is to say how big is a circle that I'm able to stick in my, or right next to the curve and make it just tangent to the point I'm interested in. Okay, so here's what I'm saying. If I've got a curve that's doing this, then the circle that I would put tangent to that point there, might be like this, So we have a particular circle that would be just barely tangent to this point. But if I had a part of my curve with a lot higher curvature, then what that would mean is that same kind of circle that's just barely tangent would have to be a lot smaller. So this is what we call an osculating circle. Osculating circle. Osculating kind of means like kissing. So it just barely kisses this point that we're interested in. And so the idea is the smaller the radius of our osculating circle, the higher curvature we have. And so the radius of this osculating circle is 1 over the curvature. Okay, so radius of the osculating circle is 1 over my curvature. Okay, so let's just do this for x equals 0, because we know from the example we just did, the curvature at 0 is equal to 6. So therefore, the radius of our osculating circle is 1/6. Okay, because x equals 0, we know that we're going to have something like this, right? So we've got x squared plus y minus k squared equals 1/6 squared. So the only question is, what is this k? All right, so what we know is that if you've got, we know that our function looks like this. So here's our function. So wherever the center is in terms of our y value, it's got to be the length of our radius down from our function value, right? So at 0, I've got to go down my radius to find the y value of my center. So all I've got to do to figure out what k is say that k, and I apologize, I'm using k here because it's the kind of the traditional center for a circle. That's different than this k here, which is my curvature, so sorry about that mix up. But f of 0, so what is the y value of 0? Minus 1/6, right? Minus that radius. So f of 0 is of course 4, so we get 24 over 6 minus a 6, so this is 23 over 6. So I'd say that my osculating circle is x squared plus y minus 23 over 6 squared equals 1/36. Now, of course, to actually graph this, we need to get y by itself, right? So this will be y minus 23 over 6 squared equals 1/36 minus x squared. And then take the square root of both sides. And again, this is not something that I'm going to ask you to do in homework, but I think is kind of a nice way of understanding a little bit more concretely what this business of finding curvature is and kind of how that relates, that the number that you get, how it relates to how much curvature you actually see in the curve you're looking at. All right, so I can punch those into my calculator, and what I get, let's take a look at this and see if we kind of believe that this is the appropriate osculating circle here. So we're going to have, I'm going to y equals, and so this will be 23/6. we'll start off with plus the square root of 136 Sorry if you hear my kids, they thought that the word osculating, I think, was funny. So they're in there mocking me as I'm trying to do this recording. All right, and so now if I go and I graph this, I don't actually see a whole lot here because this is, remember, our radius is only 1/6. So I'm not going to be able to see much. So I want to really zoom in on this thing. So let's take a look, not negative 10 to 10. Let's go just negative 1 to 1 in our x. And then maybe in our y's, remember, this is all happening right around y equals 4. So let's go from, let's say, 3.5 up to 4.5. And that should give us a much better view of what's occurring here. All right, and of course, it's always tricky when you're graphing circles in just function mode on the calculator, because as things get really steep, it tends to cut them off, right? Because it's just the calculator at some point has difficulty with its algorithms plotting those really steep parts. But you can just imagine it connects up. And it seems like this circle here does a pretty darn good job of just coming up and just kissing that point at x equals 0, at the point 0,4, and just being tangent to it there. And that circle really does a good job of mimicking the curvature right around that particular point. All right, so now let's backtrack to page 8 here. So this will be kind of the last topic we take a look at. So we're going to introduce this idea of the unit normal vector, okay? Before we do that, though, we need to make an observation. So it turns out that the unit tangent and its derivative are always orthogonal to one another, okay? And the reason that that's the case is because of the product rule here. So if I take the derivative with respect to t of the unit tangent dotted with itself, I know I have to apply the product rule to that, right? Which would mean take the derivative of the first times dotted with the second plus the first dotted with the derivative of the second. But of course, these are identical to one another, so this is just 2 t prime dotted with t. Okay, so we know that that's true on the one hand. On the other hand, if I take that same derivative, the derivative of the unit tangent dotted with itself, then I can also say that that's the derivative with respect to t of, remember, something dotted with itself is equivalent to its magnitude squared, okay? But remember that the unit tangent vector always has length 1. So because of that, I'm just taking the derivative of 1, right? 1 squared. And the derivative of a constant is 0. So what that means is that this dot product of t prime and t, it has to be 0. And if it's 0 all the time, then we have no choice but to say that the unit tangent vector and its derivative are always orthogonal. Okay? So, because they're always orthogonal, we call the unit vector t prime over its magnitude the principal unit normal vector, because it is normal to the unit tangent vector. So in this picture down here, here's what it looks like. We know that the unit tangent vector is a good approximation of the curve near the point that it's being produced at. And so it, kind of points along the curve, at least for a little bit. This principal unit normal vector then is normal to the curve there. It makes a 90-degree angle with that unit tangent vector. And then there's one other vector that you'll often see described with these two, which is called the binormal vector. If you cross the unit tangent and the unit normal vector, you get this thing called the binormal vector. And when you take these things all together, what it produces is kind of a new set of axes that are mutually orthogonal to one another that is kind of going along your curve, right? So it's almost kind of like this is like a z-axis, and maybe this is like a y-axis, and this is like an x-axis. You know, that's the kind of the idea here. It makes kind of this new set of axes. T and N create what's called the osculating plane, right? So we were just talking about an osculating circle where your the circle just goes and kisses that part of your curve. So the osculating plane is just where your curve is just kind of kissing this plane. Or another way of saying it is that near the point, the curve is kind of sitting in that plane for the most part, at least for a little bit of time. So that's what this thing does. In terms of your homework and what I'm going to expect of you, I'm not going to do a lot with this. This is some really interesting stuff that if when you go on to study differential geometry and things like that, you'll see a lot of this. We're just kind of doing the basics here. So all I really want you to be able to do is if I ask you to calculate for me the unit normal vector, could you do that? Okay, so let's just do one example of something that I might actually ask you to do. So this is our work from example 4. So I'm going to kind of cheat a little bit on this. I want to find the unit tangent and the unit normal vectors for this this one here that we refer to as a twisted cubic at the point 8, 8, 32 over 3. Okay. So remember, anytime we're doing something like this, we're saying we want to do this at a point, then we've got to figure out what t value that point goes with. So first order of business is to say, okay, I know that 2t needs to equal 8. I know that t squared over 2 needs to equal 8. And I know that 4/3 t to the 3/2 has to equal 32 over 3. So start with the easy stuff, right? We can see here t equals 4. If I put 4 in here, does this work? Yes, because I'd have 16 over 2 is 8, so it works out there. If I put t equals 4 in here, you're going to get 8 when you raise it to the 3/2, and so that'll be 32 over 3. So t equals 4 is what goes along with this point here. So we need to find the unit tangent at 4. We need to find the unit normal at 4. So I'm going to rely on what we did earlier. So from example 4, we've already done a lot of this hard work. We can see that t of t, the unit tangent is 2 over t plus 2, t over t plus 2, 2 root t over t plus 2. And we also know that t prime was equal to negative 2 over t plus 2 squared, 2 over t plus 2 squared, and 2 minus t over the square root of t plus 2 squared. And then we also, as a result of finding the curvature earlier, we also had to come up with the magnitude of t prime. And remember, that was 1 over the square root of t plus 2. So what that means, remember, is that our normal vector, our unit normal vector, is going to be t prime of t over the magnitude of t prime. So it's just me taking this vector divided by this. And so that's going to be, well, we're going to have, let's see, let's write it out. Negative 2 over t plus 2 squared, 2 over t plus 2 squared, 2 minus t over square root of t plus 2 squared. But then you're going to divide all that by 1 over the square root of t plus 2. And so then you're, of course, going to flip and multiply. And so when we do simplify that, what we get is negative 2 square root of t over t plus 2, because we get a t plus 2 on bottom canceling with this t plus 2. 2 roots of t over t plus 2, and then 2 minus t over t plus 2. But of course, we wanted to figure this out at 4, right? So we just plug 4 in for my unit tangent. And when I do that, I get 1/3, 2/3, 2/3. And then for my unit normal, I get negative 2/3, 2/3, negative 1/3. So that's my unit tangent and my unit normal vector that I just found. Okay, but it also asked me to do something else. It also wanted me to find the equation for the osculating plane. Okay, so remember, we defined our osculating plane, going back to that previous picture, as the plane that contains these two vectors here, right? It contains this vector and it contains this vector. So that's going to be our osculating plane. So if I know that my plane is supposed to contain these two vectors, this is a game we've played a lot. We take the cross product of them in order to find the normal vector, right? So the normal vector for our plane, which by the way, we could just find that thing we called the binormal vector, right? That's what it is. It's the cross product of these. So I'm going to take the cross product of these two vectors. And when I do take that cross product, what I'm going to get is the following. So I'm going to get, let's see here, negative, negative 2/9 minus 4/9, so negative 6/9, negative 3/9, 6/9, right? Which is going to be negative 2/3, negative 1/3, 2/3. All right. So with this works as our normal vector, and so we know that in order to come up with the equation of the plane, we can just take these times x minus the x value we're at, that times the y value we're at, and then 2/3 times z minus the z value we're at. And that is going to give me the osculating plane for this curve at this point. Okay, I think that before we wrap things up here, this would definitely be worth our time to go ahead and plot. So I'm going to put this in our calculator or in our 3D grapher. So we'll have, let's see, we've already got that typed in. Now let's see, I'm going to go just a little bit further here. Okay, and so let's go ahead and type in this plane. Now in my notes here, I already kind of, don't be alarmed by the fact that I'm typing in the equation that I am. I just did some work earlier in my notes to make it so that I can easily type it in. So getting z by itself and everything. And so look at what we have here. Let's zoom in quite a bit here. So maybe don't graph quite so many values of t. So let's maybe just go like 3 to 7, maybe. Well, let's see here. This was supposed to be t equals. Oh, okay. Actually, I did want to have all that, but I think I just need to make my plane greater. So let's see. Let's change that to like a 15 and a 15. There we go. Okay. And so you can see that actually for a good long while, this curve is lying right in this plane. It takes it a while actually to really get further away from it. Over here, it kind of starts to break away. And in fact, if I go, let's see, I can't really go negative. So this one actually does. You can see it's above the plane there, but then it kind of settles down into that oscillating plane pretty well for a good long while.